In this video, we'll talk about signs of trigonometric functions in different quadrants, basic trigonometric identities, and special triangles. Let's observe behavior of sine, cosine, and tangent exactly at quadrantal angles. First, let's consider the 0-degree angle or 360-degree angle. Both of them have the same initial and terminal side. Let's pick an easy to work with point on this terminal. For example, 1, 0. So it's easy to read what the x, y, and r values are for this particular point. X is 1, y is 0, and r is also 1, since this point is chosen to be one step from the origin, right? Therefore, using the definitions of sine, cosine, and tangent in terms of x, y, and r, it's easy to find the value of sine of 0 or 360, it is y over r. So it's 0 over 1, therefore it's 0. Cosine of 0 or 360, it is x over r. So it's 1 over 1, therefore it's just 1. And tangent of 0 or 360, it's y over x, therefore it's 0 over 1. Again, the value is 0. Let's find the values of our trig functions of the angle 90 degrees. Again, let's pick an easy point, 0, 1, at the distance 1 from 0, so we can list what's x, y, and r that corresponds to this point. X is 0, y is 1, and r is 1 as well. Again, sine of 90 degrees, it's y over r, so it's 1 over 1, therefore it's just 1. Cosine of 90 degrees is x over r, so it's 0 over 1, therefore it's just 0. And tangent of 90 degrees is y over x, which means 1 over 0. Oh, that can't be done. Therefore, tangent of 90 degrees doesn't exist. We write D and E, doesn't exist. Okay, so we already know how to do it. You may want to pause the video and try to finish the next two rows on your own. To find the sine or cosine or tangent of 180, let's pick a point on the terminal of 180 degrees. For example, a point -1, 0. Okay, that's an easy point. We can pick any other point, but this one is just the easiest because the r is 1. So let's list x, y, and r. X is -1, y is 0, and r is 1 as before. Okay, sine of 180 degrees, it's y over r, so it's 0 over 1 means 0. Cosine of 180 degrees is x over r, so it's -1 over 1, therefore the value is -1. And finally, tangent of 180 degrees is y over x, so it is 0 over -1, meaning 0 overall. Finally, all trig functions of 270 degrees. Well, this time we are looking at one point on the terminal of 270 degrees, which is the negative y-axis. So again, we can choose an easy point, for example, 0, -1, and we can list x, y, and r for this particular point. X is 0, y is -1, and r is 1. So sine of 270 is y over r, therefore it's -1. Cosine of 270 is x over r, so it's 0. And tangent of 270 is y over x, so it's -1 over 0. Again, it doesn't exist. Okay, so those are the special values of our functions at quadrantal angles. Notice that tangent at 0 and 180 is equal to 0, while tangent at 90 or 270 degrees doesn't exist. Next, let's observe signs of x, y, and r in different quadrants to find the signs of trigonometric functions in each quadrant. We're going to fill up this table. So if our angle theta is in quadrant 1, we are really talking about acute angles between 0 and 90 degrees. What is the sign of the sine function or cosine or tangent of any angle from the first quadrant? Well, let's observe that in the first quadrant, both x and y are positive. Obviously, r is always positive because that behaves like a radius. It represents the distance of a point from the origin. And distance is always positive or 0, but we're talking about a point that is inside the quadrant, not at the origin. Okay, therefore, if all of our three letters are positive, the quotients of any two of them are positive as well. So our trig functions in the first quadrant are all positive. Okay, now let's see what's going on in the second quadrant. What do we know about the sign of x? Well, x is always negative, and y and r are both positive, right? Therefore, when the quotient x over r, y over r, or y over x is negative, only when it involves x, because x is negative. So the ratios that involve x are cosine and tangent. Therefore, these two functions are negative, but sine is positive in the second quadrant. Next, what do we know about x and y in the third quadrant? Both of them are negative. So x and y are negative, but r, as before, is positive. So which quotient will be negative? Well, y over r, because one variable is negative, so this is negative for sure. X over r is also negative, but y over x is positive because we are using two negatives. So the tangent is positive, however, sine and cosine are both negative in the third quadrant. Finally, the fourth quadrant for angles from 270 till 360, the y-coordinate of any point in this quadrant is negative, but the x-coordinate and also r is positive. So what are the signs of our functions? Y over r is negative, x over r, since both variables are positive, the quotient is positive, and y over x, since the y is negative and x is positive, altogether it's negative ratio. So that's how our trig functions behave in different quadrants. Observe the following. In the first quadrant, all functions are positive. So let's write all. In the second quadrant, only sine is positive. The other two functions are negative. So here we will write sine. In the third quadrant, only tangent is positive. So we write tangent. The other two functions are negative. And in the fourth quadrant, only cosine is positive. The other two functions are negative. To memorize those signs, we can follow the first letters of those words. If we start reading them counterclockwise, starting from the fourth quadrant, they spell cast, C-A-S-T. This will help us remember which functions are positive in a given quadrant. In the next example, we're supposed to identify the quadrant or quadrants of the angle theta given the information. What do we know here? We know that sine is positive, and we know that cosine is negative. Let's sketch a system of coordinates, and we're going to highlight the quadrants that satisfy the first condition, let's say in yellow. So in which quadrants sine is positive? Well, sine is positive whenever all functions are positive or whenever sine is positive, so in the first and second quadrant. Let's highlight it. Those are the two quadrants that make sine positive. And second condition, where do we have cosine negative? Well, let's look again at our cast. In the first quadrant, all functions are positive, so that's not good. In the second one, only sine is positive, so yes, cosine will be negative. Second quadrant for sure, right? Third quadrant, only tangent is positive, therefore cosine is negative, so it satisfies this condition, therefore this quadrant also belongs to our solution. Okay, and the fourth quadrant, cosine is positive, so it's not good for us, right? Okay, therefore we are searching for the region when both conditions are satisfied. So we are really searching for the intersection of these two conditions, right? The intersection, the overlapping part, is the second quadrant, right here. Okay, so here's our answer. We can say theta belongs to quadrant 2. Let's try to do the second question on your own first, and now check if you've got the same answer. Again, we can highlight maybe in orange the region that satisfies this condition, in which two quadrants sine is smaller than 0. In the top two, sine is positive, right? Like before. Therefore, in the bottom two, sine is negative. Okay. Now, let's say in blue, we'll mark those regions where tangent is negative. Well, tangent is positive in the first and third quadrant, therefore it's negative in the second and fourth. Okay, so that's the region, and this one. As we see, the overlapping part, both conditions are satisfied just in the fourth quadrant. That's our solution. This is fourth quadrant, and we can say angle theta belongs to quadrant 4. Here we go. What do we need to do in this example? Using definitions in terms of x, y, and r, find the values of the other trigonometric functions of the angle theta, knowing that cosine of theta is negative 1/4, and also that theta is in the second quadrant. Okay, do we remember the definition of cosine of theta? It is x over r. Therefore, if cosine of theta is given as negative 1/4, we can assume that r is 4, as it must be positive, and x is negative 1. Now we can list the x, y, and r. X is negative 1, r is 4, and y comes from the Pythagorean equation. X squared plus y squared equals r squared. Therefore, y by itself is square root of r squared minus x squared. Okay, let's follow this rule. We have square root of r squared is 16 minus x squared is 1. So altogether we have root 15. Should we take y positive or negative? Well, we check this condition. Theta is in the second quadrant. So let's see. Any point in the second quadrant has its y-coordinate positive. So we have positive root 15 here. Okay, now we're ready to give the values for other trig functions. What's sine of theta? Well, sine is y over r, so it's root 15 over 4. And what's tangent of theta? That's y over x, root 15 over negative 1. So we end up with negative root 15. And it's done. Let's see another example. As usual, I will encourage you to try it on your own first. Recall the definition of sine of theta in terms of x, y, and r. This is y over r. So since y over r is root 3 over 2, and r is positive, which is 2, we can figure out the x, y, and r. We know that r corresponds to 2, the y corresponds to root 3, and x can be calculated from Pythagorean equation. So it will be x equals root of r squared minus y squared. However, this root could be positive or could be negative. How do we decide about this sign? Well, by looking at the second condition. Tangent is positive. So if we sketch the system of coordinates to recall which quadrants tangent is positive in, well, thinking about cast, right? The tangent is positive here and there. Okay, first and the third quadrant. Since we know that y is positive, it has to be the first quadrant, isn't it? So this x is root of r squared, which is 4, minus y squared, which is 3. Therefore, it's root of 1, so it's really 1. Okay, let's write it 1 here, and now we're ready to give the answer for other functions. Cosine of the same angle theta is x over r, so it's 1/2, and tangent of the angle theta is equal y over x, so it's root 3. Now, notice that the Pythagorean equation x squared plus y squared equals r squared and definitions of the three trigonometric functions lead us to the following identities, very useful identities that it's worth to memorize. How can we prove those identities? How do we know that this is true? Let's see how can we develop the first identity, starting with the Pythagorean equation. Okay, let's start with x squared plus y squared equals r squared, and then we'll try to connect this equation with the identity we want to prove. Since on the right-hand side we have 1, why don't we divide the whole equation by r squared to make it 1 on this side, right? So let's divide the other side by r squared as well. And what do we observe? Well, here we have x over r squared, and then it's plus y over r squared, and then it's equal 1. Well, it looks like nearly the same, isn't it? Because this x over r is a definition of cosine. So we can replace this ratio x over r by cosine of certain angle theta, and then we square it. While this ratio represents sine theta, which is squared, right? And overall this equals to 1. Now if we use commutativity of addition, this equation is already equivalent to our identity sine squared plus cosine squared equals 1. This identity is also referred to as Pythagorean identity, but trigonometric version of it. Now let's see how can we prove the second identity. This time let's start with the right-hand side, sine theta over cosine theta, and we'll try to find out how much is that equal to if we use the definitions in terms of x, y, and r. Sine of theta can be replaced by y over r, while cosine of theta can be replaced by x over r. Now if we convert the main division into multiplication by the reciprocal of the divisor, r over x, then we can see that r can be reduced, and we really end up with the ratio y over x, which represents our tangent, isn't it? So the identity is proven. Another interesting thing to notice is that the cofunctions of complementary angles are equal. For example, if we have a triangle ABC like this, with the measure of angle A being alpha and measure of angle B being beta, then sine of alpha is opposite over hypotenuse, so it is A over C. Cosine of beta is adjacent over hypotenuse, so it is also A over C. Therefore, sine of alpha is the same as cosine of beta. But we know that beta is the same as 90 degrees minus alpha, isn't it? So just looking at this right-angled triangle, it's easy to say that for acute angles, the equation sine alpha equals cosine of 90 minus alpha holds. The cofunctions, sine and cosine, those are cofunctions of complementary angles, are equal. Okay, that's good to remember. Therefore, we know that, for example, sine of 18 degrees is the same as cosine of 72 degrees, because 72 is 90 minus 18. That also means that cosine of, for example, 15 degrees would be the same as sine of 90 minus 15, which is 75 degrees. Neat, isn't it? Now let's take a closer look at angles 30 degrees, 45 degrees, or 60 degrees. Those angles play an important role in trigonometry. They are frequently used in applications and when we are asked to give the exact values of the trig functions. So how to find the exact values of our trig functions at these special angles? Well, we have two special triangles that will help us to develop and memorize those values. The first triangle comes from cutting a square along the diagonal. This way, we obtain a right-angle isosceles triangle with the acute angles of 45 degrees. Using the Pythagorean equation, we can prove that the diagonal of a square with the side of x units has the length of x root 2 units. Therefore, we will be able to tell the exact values of sine, cosine, and tangent of 45 degrees. The second triangle, quite often referred to as golden triangle, comes from taking half of equilateral triangle. Therefore, this is also right-angle triangle, with one of the acute angles being 60 degrees, because it comes from equilateral triangle, and the second angle is half of 60, so it's 30 degrees. This is the 30, 60, 90 degrees triangle. It's called a golden triangle. Now the relations between its sides are as follows. If we denote half a side of the equilateral triangle as x, then the full side of this equilateral triangle is 2x. And then, using the Pythagorean equation, we can find the length of the height to be x root 3. So x, 2x, and x times root 3. Let's prove those relations. First, we're going to prove that the diagonal in a square of the side x is equal to x root 2. Let's denote the diagonal of the square by the letter d. Using the Pythagorean theorem, we have d squared equals x squared plus x squared, right? Now we are solving for d in terms of x. So we can put square root on both sides, resulting in d on this side, and here we have square root of 2x squared. Okay, but now we can take the x out of the root, so we have x root 2, and the relation is proven. Yes, the diagonal of a square with the side x is equal x root 2. Now let's prove the relations in a golden triangle. If we denote half a side of the equilateral triangle by x, then the full side is of the length 2x. Now we can mark the height of the equilateral triangle by h, and therefore from Pythagorean equation applied to this right-angle triangle, we have h squared plus x squared equals 2x squared, right? We are solving for h in terms of x. So h squared would be equal 4x squared on this side minus that x squared from the left-hand side, right? Then by applying square root on both sides, we have h on the left, and here we have square root of 3x squared. Again, if we pull the x out, we have x root 3. So yes, indeed, h is equal to x root 3. So it's proven. Finally, let's use our special triangles to complete the following table of values. We're going to develop exact values of sine, cosine, and tangent of those special angles 30, 45, and 60. Let's start with the 45 degrees row. We're going to refer to this half a square triangle, 45, 45, and 90. If the two sides of the square are marked as 1 unit, so 1 unit here, 1 unit there, therefore the diagonal of the square has length root 2, isn't it? So we know that sine of angle 45 is opposite over a hypotenuse, so it's 1 over root 2. We can write 1 over root 2, or equivalently, let's do it on the side, 1 over root 2. If I multiply the top and the bottom by root 2 to get rid of irrationality from the denominator, I end up with root 2 over 2. So the value is 1 over root 2, or equivalently root 2 over 2. And this happens for both sine and cosine, because cosine is adjacent over hypotenuse, so it's still 1 over root 2. Okay, so 1 over root 2 or root 2 over 2. Both are fine. Finally, tangent of 45 degrees is opposite over adjacent, so it's just 1. Very nice value. Easy to remember. Tangent 45 is equal to 1. Now let's think about 30-degree angle. So we are referring to half of the equilateral triangle, the 30, 60, 90 type of triangle. If the shortest side is marked as 1, therefore the hypotenuse will be double the 1, so it's 2. Okay, this is like full side of our original equilateral triangle, isn't it? And this side represents the height of the equilateral triangle, so it is half a side times root 3. Therefore, it's just root 3 because half a side was equal to 1. So 1, 2, root 3. Very easy to remember. 1, 2, root 3. Okay, let's focus on angle 30 degrees. Sine of 30 is opposite over a hypotenuse, so it's 1/2. And we mark it 1/2. Cosine of 30 is adjacent over hypotenuse, so it's root 3 over 2. Root 3 over 2. Great. And finally, tangent of 30 is 1 over root 3. Again, 1 over root 3 can be rationalized. As before, we can do it on this side. 1 over root 3, if we multiply by root 3, the top and the bottom, we end up with root 3 over 3. So either 1 over root 3 or root 3 over 3, that's equivalent value. And lastly, 60-degree angle. Sine of 60 degrees, sine of this angle, is opposite over hypotenuse. It's root 3 over 2. Root 3 over 2. Cosine of 60 degrees is adjacent over hypotenuse. It's 1/2. And tangent is opposite over adjacent, so it's just single root 3. Great! Those are the exact values of the three trig functions at special angles that can be obtained directly from the special triangles. So I will encourage you to memorize the special triangles in that form: 1, 1 root 2 and 1, 2 root 3. One more thing to observe. Notice that sine of 30 is the same as cosine of 60, and similarly cosine of 30 is the same as sine of 60. This is because the cofunctions of complementary angles are equal. Also, notice that the value of tangent of 30 is the same as reciprocal of the value of tangent of 60. So tangent 30 degrees, it's the same as 1 over tangent 60 degrees. Or we can rewrite this equation as tangent 30 times tangent 60 is equal to 1. So we multiplied tangents of complementary angles and we got 1. Is this a rule? You may want to investigate it using a calculator. For example, check if tangent 10 times tangent 80 is equal to 1, or some other complementary angles. Investigate if tangent alpha times tangent 90 minus alpha would be 1. True or not? See if this equation will hold for various alphas.